Let me see. And then I think now it's recording. Yes, now it's recording. So you were actually studying the least square method, if you remember, in the previous class. So you saw essentially that the least square method is actually very suitable when you have actually some complications with the numbers of equations. So if you remember, one of the advantages that you had is that when the number of equations exceeds the number of unknowns, of course, you need a method to be able to solve it. So one of the things that you observed was this simple example, if you remember or you recall it. So in this case, you cannot actually solve it with the Gaussian elimination, right? Because you don't have a square matrix A, right? So you for the Gaussian elimination or the other methods that we were talking about in the previous classes. So you need actually a square matrix A, a vector X, and a vector B. So in this case, you cannot actually solve it. So that's why we call out the least regression method. So, and remember, you just went actually through this. So this is the equivalent part of this system. Then you went to the example, and then they show you how to actually compute all the least square actually a method. So you have this one, then you go to the example, you have this one, which is not a square, of course, and then you went through the transpose, you create actually this transpose times A, which is pretty common. You have actually a square matrix, and then you have the transpose multiplied by the B vector of the constant of the system, and then you obtain this one, and then already you solve this one, and then you obtain sequentially, of course, this by the Gaussian elimination or by any other method that you already know. So we see that it's actually a very simple, if you think about it, a very simple application of the least square. So it's a very simple. So you went back to the least square substitution, remember? So you went and substitute, and then you obtained, and this one is not equal to this one. So in this case, you actually have to measure the success of your data. So you calculate the residual, which is B minus minus I minus X, the vector X bar, which is already the solution that you provided here. And then you obtain the residual. So you have actually an error. So the least square method is subjected to an error. So it has a deviation between the observations and the real data. So that's why it's an approximate method. So we use it to approximate data. It's actually pretty much successful it's pretty much related to what we do when we use a polynomial interpolation. If you remember, for n values, you see that you will produce a polynomial with degree n minus 1. However, you can approximate it with a polynomial of n minus 2, and it would be also an approximation, right? So it's an approximate method, as the polynomial interpolation is when you use a lower degree instead of the n minus 1 degree that used to actually fit the whole set of data set. So that's what we want to explain in this. Least square is a method used to approximate the solution, and is suggested to an error. So this is the calculation of the error. So we find actually different measurements. This is the deviation, the residual as such. We express also the error as an Euclidean distance. So you also have this one. You have the square error, which is another type of error. So you also saw that we have the root mean square error. We compute this one as well, and also can be calculated as this one. So you already saw this one and calculate for the example one. So you just calculated the SE here, the 2 norm, which is this one, and then the root mean square error by this operation. So you see that it's actually very, very simple. Same thing, you use this one, we use the normal equation for this one, and then you get the solution. You obtain the residual vector once again, and then you compute the norm, the 2 norm, and so on and so on. So additionally, in that class, we see actually the fitting model data. So we see that this actually, this is what we call the residual here. We have the E1, E2, E3, E4, and E5. So that could be quantified as an error. So that's how we calculate the residual. But if you think about it, in this case, actually give you an idea of how you create a regression model. So a regression model is actually a least square base method. Okay, so that's what I wanted to come back to this type of things, because of course we feed this data with this one, and then we did the same procedure with what you have already known. We create errors and we just continue. So essentially, I gave you 3 steps mainly to run the least square method. It's the 1, 2, which is choose the model, because we have to choose a model. So in this case, a model was this one, actually, the baseline was this one. But you have to choose a model. Here, for example, a model was chosen. In this, you have to choose a model, then you have to force the data to feed the model to feed the data, and then you solve the normal equations. So this is what you have obtained. So this is an approximation here. This is another approximation right here. So, and this is what we did in the exercises to use the model, which is a linear model. You use it, you solve it, and you quantify the error. The second was actually a square, a polynomial approximation, and then you calculate again, once again, all the values, calculate the value of C, and then you obtain the errors. So it was a very simple method. It's actually one of the simplest methods I can tell you. So, and also we provide commands to verify your equations. So this is how you actually do it. X0, Y0, and then polyfit, and then you plot it. So it's essentially a way to actually corroborate that you're doing things all right. And then I give you exercises, such as this one. So this is the exercises that you already have. But then today we're going to actually have another view. Today we are actually still continue with the least square method, but we're going to see a more simplistic and more applicable explanation of this. Okay. So one of the things that, of course, I actually can't advise you, it's the use of the technology. So we're going to actually approximate using the least square, but now we're going to talk about regression. So we're going to use the least square method to regress the data, which means, of course, feed the data through a line or through another polynomial, but using technology. We are no longer using actually the complexity of these things, but rather to be more applicable, and you won't have the tools to actually do this by hand. Okay, so you have a YouTube model, YouTube video to watch if you want to actually refresh your view about the least square. However, you have actually the video I already give you. So I think with my video, it's just enough. So you can watch it if you want to do it, but it's up to you. So remember that the least square was actually appropriate when we fit, or when we choose a model, such as this one, choose a model, and then we need a matrix, the component of the matrix that we want to arrange, which is actually formed by the values of the date. And then we have a CD vector and a V, which is actually the coefficients that are, of course, valuable to actually have 1, 5, and -2. So once we have these matrices, of course, we solve for this one using what we have already learned in the equation. We just calculate the transpose, and then you, as you already know, you calculate the x dot, and then the x dot is equal to the solution CD equal to this. So this is what you already know, right? You already know this one. You already know how to do it. It's a very simple exercise. You have to choose the model, as I said in this slide. You have to right here choose a model. I chose this model. CT plus DT squared equal to Y. So remember that all these things actually find the quadratic model to this equation. So you'll see that this is a very simple way to do it. So then you have to force the model to feed the data. We are actually forcing this model through this. And then, of course, you have to solve the normal equations. which is these normal equations. You solve it by multiplication of two matrices, and then you obtain this one, and then you solve it for this. So it's very simple, and you obtain the final equation, right? So, but then we have to be more specific now. So, for example, we're going to move to a more sophisticated data. So, in general, for example, if you want to actually go through applications. So, in engineering or in science, we often use linear regression to estimate variables that linearly depend on a second variable. For example, if we can consider this application. So, for example, we have different countries right here, and then we have the fat intake, el consumo de grasa, and then we have the cancer death rate. So we see that the fat is actually related. It is related. You see that the more fat you consume, so there are actually you have more probability that you die by a cancer. So you see, for example, in the US and Canada, which are actually the higher numbers of fat intake, you see that they have the highest rate of dead people by cancer. So that's actually pretty scary if you think about it. Well, we don't have Mexico here, but I'm assuming that we're very close to Canada and the US. But then you see that it's linearly related. So it actually, these points are the dots. So this is the data that we want to actually fit here in this example. So how do we do this? So how do we do this? I have actually, give me a second. I have the examples. I think this is the example. Just let me just open this. It's a new computer, so I have to download all my iCloud. It's supposed to be faster, but it takes a while. ¿Tienen alguna pregunta acerca del least square method del que vieron la clase pasada? Por cierto, en lo que se descarga. ¿Tienen alguna pregunta? No, se están durmiendo.
No, profe. Al menos yo sí lo entendí.
Ok. Bueno, entonces les voy a mostrar dos formas de hacerlo, ¿no? Sí, aquí están, sí son estos. Ok, so tenemos dos formas de hacerlo. Por ejemplo, this data is actually, it's taken actually from a journal, the Cancer Research. The cancer per rate is per, so this is actually how much? Like 100,000. And the fat intake is in grams. So you per rate is actually, you have the rate equal to this amount. So if you think about it, is this one in Thailand, you have 27 grams per capita per day. So you're talking about that we eat, for example, if we eat 27 grams of fat, our cancer rate would be equal to 1. So but in the US, cancer rate is 1 times 100,000. So for each 27 in Thailand, 100,000 people are going to die by cancer. So this is what is saying. Cada vez que nosotros en Tailandia, por cada 27 gramos per cápita per day, por día, o sea, si tú prácticamente uno de ustedes toma 27 gramos, está contribuyendo a una estadística en Tailandia, por supuesto, de 100,000 personas por muerte de cáncer. En Estados Unidos, imagínense, prácticamente estamos haciendo, o sea, por cada 148 gramos de grasa que consuman al día, una persona está contribuyendo a una estadística de 22 por 100,000. ¿Cuánto es 22 por 100,000? Sería 2,200,000 personas que se van a morir de cáncer. O sea, es algo bastante crítico, ¿no? ¿Ok? Entonces, hay dos formas de hacerlo muy sencillo. El primero, voy a borrar en este caso esta tabla. El primero es el siguiente. Entonces, el primero es el siguiente. Prácticamente yo grafico los puntos. Si quisiéramos hacerlo más aplicado, por supuesto, grafico los puntos. Prácticamente tengo aquí, y le voy a poner un color, digamos, aceptable. Esto es fat intake in grams. And this is actually, what is this one? So cancer death rate. Cancer death rate. And the units of this one is going to be grams, and this is going to be a rate of 10 to the power 4. Just call it 10 to the power 4 people. Where is this one? 10 to the power, no, this is another one, power, oh. I don't know how to the power 4, no. Sorry, it's a new keyboard, so I'm not used to get this kind of, so Alt, this one, 4, no. No. So like this. I'm sorry. So this is actually the plot. So if you want to be more applicable, of course, you just can actually do this. And then you go to add trend line. And you will see that you have actually the option of in Excel, use the exponential, linear, linear, logarithmic, polynomial, power, and moving average. So this is one example, but also, for example, we can actually display the equation here and then the R squared. So you see that the line actually captures 90% of the variability of the data here. So we're talking about that the cancer death variability is actually explained 90% by the fat intake per grams. That's what I'm talking about in this one. So if you actually want to modify this trend line, for example, you can make it exponential, but you see that the R square is actually less. So it's actually more linear. If you want to make it polynomial, of course, you see that this is actually less. But here we have actually logarithmic, and then you have the polynomial. So polynomial degree 2, it actually gets a very good one. But remember, the more degrees, for example, you have 1, 2, 3, 4, 5, 6, 7. So in this case, we have a polynomial of degree 6, and it's going to be, this is actually what we did in the previous classes. So this is the polynomial that fits all the data. So it's n minus 1. You have 7 points, and you have a big chunk of the equation. And if you see, the R squared is equal to 1. So this would be the ideal model, but it's not the ideal model because you have it's a very long equation. So it's not the best one. So we don't want to actually do this. So instead of using a polynomial regression, polynomial interpolation, sorry, we better actually, we use something more realistic, a linear model. So it's actually 91% of the data. So that's a good approximation. So that's what we can do. Okay. So this is one of the examples, but you can ask me, Professor, okay, I agree with you that this is actually a very good tool, but how do we get these things? This is important. How do we get this point? Because I can use just Excel and give some example to you, and then you will get the answer very quickly. But instead of doing so, there's just another. Instead of doing so, what we need to actually, it's find a method to make it more precise and faster. Instead of just doing the least square, we're going to provide some of the examples. So we'll see the following method. So this is how we do it. This is in general how we would do it if we have the Excel spreadsheet. And then we can actually fit a model using the following scheme. So we have to actually get an R value, okay? An R value that is gonna be formed by this equation. So if you think about it, just for linear regression, for a linear model, so we have X and Y, which is the data, and N is equal to what? To the number of points. Of course, this is the summation of what? Of the multiplication of X and Y, and then the multiplication of the summation of the X times the summation of Y, then N, or the square root of all this chunk, which is actually the number N, number of observations, or the data points, times the summation of X squared, minus the the summation of X squared. So, and then we have the same thing for Y. So we have actually this equation, which should give you actually a value of R. This is a coefficient R. So in general, we can actually do it like with some data set that I prepared. For example, so we can do it like this. So here I brought the equation. This is the equation right here. So in general, we need this equation and these two equations. Okay, so and A and B is going to be respectively, is going to be actually A is going to be the constant value and B is going to be the coefficient for the linear model, the X value. So it's going to be the first coefficient and this is going to be the constant value. But to apply this expression, it's just very simple. So I'm going to actually delete this for you to actually see it from the very beginning. So these are the data sets. So it's the same thing. So I'm going to delete this for you to see how this goes. So you have the data set. This is 27. You just put it here, and then have to calculate actually all these things. Of course, you know beforehand that N is equal to how many? 1, 2, 3, 4, 5, 6, 7. So we have the value of N. So N is equal to 7. Right? So now we need to actually calculate the summation of X and the summation of Y. So in general, I want to say summation, or this is equal to summation of X, enter, plus summation of Y. Here you have it. So this is the summation. We have this one and this one, right? And then we see that we have actually the summation of X squared and the summation of Y squared. So we have to calculate actually the X squared, which is going to be equal to X squared. Oh, I don't have this. Man. So if I don't have this one, so I would. ¿Alguien sabe cómo colocarle el gorrito en el teclado español? El gorrito que te da la potencia.
Con la tecla que está al lado del espacio, el Alt GR.
Sí, profe, creo que es con Alt y poner ahora donde está el
Con
gorrito.
Control Alt, ¿no? Bueno, en Windows es Control Alt y el gorrito. No sé.
A ver, Control Alt y el gorrito.
Ajá, la tecla del gorrito. Ajá, ahí,
So, ahí
ahí.
está. Listo. Okay, so thank you very much. So we have the square, and then we have, of course, to run this down. Here we have all the square values of this one, and then we just calculate the summation. So we calculate the summation, and then we have the summation right here, and we do the same for Y. So Y is equal to this, and then we're gonna compute again the square of this one. And same thing. So we calculate the square of all of this, of all the Y values, and then it's going to be equal to summation of all this range. Enter. So you get the summation, right? So we already have from this equation, we have this term, we have this term, we have this term, and n. So we only need actually the summation of x, y, and of course we need also the summation. Well, the summation of x, y squared is fine. We have this one already, and that's it. I think we just need the xy summation. So for that one, we're going to multiply x times y, and then we're going to run this down, x times y, and then I'm going to make the summation of this. So we just run it, whoops, and then we get it. So for this one, we have already everything to actually run this thing. So in this case, I'm going to actually delete this. So to make actually some statistics just defining this topic. So the standard deviation of this one is 4276. The standard deviation of y, this is standard deviation, and then you have the mean value of this one, and then the mean value of this one. Okay, so just to create this one. So remember that this is the average of this one. This is the average of this one. Standard deviation, which is actually ST deviation dot p of y, of course of x as well. So we have these terms because we're going to be using it to calculate some other variables. Okay, so in general, when we have this one, so we can say that R parentheses, we're going to use this equation. So I'm going to use n times the summation of xy. Which one is the summation of xy? Is this one, right? This is the summation. Okay, minus the multiplication of the summation of x, times the summation of y. Right? This is the numerator, right? So just to clarify, I just want to make sure that this is the summation. Yeah, this is the summation. So we have this one already on the top. And then we have to divide by parentheses. I'm going to actually make this to the power 0.5 because this is square. So power, 0.5. Right? And then we have, again, n, this one, n times the summation of x squared, minus the summation of x to the square. So it would be actually the summation of x, this one, the square, like this. So, and you see that we also need a parenthesis because this is another multiplication. So we need a second parenthesis, then multiply times this part, which is n again, and another parenthesis. Another parenthesis right here. So it's n again times the summation of y square. So the summation of y square, right? Minus the summation of y square. This. So now you have all the equation right here, and then you get a value of 0.95. Okay, so for these things, for example, it's easy to get it. We have the value R, and then what we need to do is actually just compute the A and B value because this is the part of the equation that we need to do. So to compute A, we use this equation. So if you see it, actually I'm using the mean of these values. So, but first of all, we need a B coefficient. So we need B, and B includes actually R. So R is equal, sorry, B is equal to R times, in this case, if you see it, the coefficient B depends on what? On the standard deviation of these two values. So the standard deviation of Y and then the standard deviation of X, right? So if we actually delete it, just to make it from 0, is equal to R times XY, SY, which is actually the standard deviation of Y, divided by the standard deviation of X. And then you get the value, 0.18. And the final value, of course, if we actually do it from 0, so this is going to be equal to Y, which is this Y, give me a second, so it's Y is equal to the mean of Y minus B times the mean of X. So we have it here. So we have the equation already formed. The linear model of the regression is equal to minus 3.9132428 plus 0.1875305. Okay, so this is the way I do it here in Excel. And then let's compare actually what we get here in the model. So you see beforehand, then this is actually, look, this is actually what? The coefficient here, minus 3.9132, is exactly the same as the Excel calculated, and the coefficient of X is equal to 1817, which is actually the same thing. So now we know what Excel is doing inside. And if actually you think about R, if you think about R, in this case, this is R squared, which is the this is the how you call the correlation coefficient, R squared, or the coefficient of determination. Sorry, this is a statistic of this. So in this case, so you can actually tell that this could be related to this R. But if we actually do this, so you say R, and we make it a square. Look at what you get. So it's 0.981, 0.982. It's exactly the same. So we can have also the R squared provided by Excel just by squaring our R value. So it's pretty much the same thing. So then if you think about it, so instead of actually, we know that this is going to be our model. So our model is actually, if you think about these terms, so I think I have the K-latex here. No, not yet. K formula. No, I don't have it. But if you think about it, so our model in general is equal to Y is equal to, as I said, A minus BX. So this is the model that we actually using for least square models. So this is the equation that you get solving all this complexity here. So this is actually what you did in general. So you got this one. This model is the same thing that we obtained. So this is the one you use. So you obtain this one by applying the least square method, and then you obtain the coefficients, C and C, the C1 and C2, and you obtain the errors. So you see that it's actually what we're doing here. So, but instead we're using Excel to a more comprehensive or a more easier application of this. So one of the things that I can actually offer you, if we want to, if you can actually, if you see here, so you have exercises to do for an assignment. So these exercises are very, very, very easy to do it. So if you think about it, so the first one is this one. This is the result. The second one is this one. This is the result. So we see that we don't have actually a good approximation. The fourth one, this one, the tuition, in this case, and credit is actually a very linear model. And the fourth one is this, in this case, the temperature. You see the relationship between the temperature and the sales. The sales, in this case, in the sales, I'm talking about the sales of the ice cream. So remember that I said we were talking about the company that Montoya has. So Montoya, in this case, has this data. And then we see at regression analysis that we explain actually 74% of the variability of the sales that Montoya has in this company. So these are examples. But what do I want? What do I want? I don't want these examples. So what do I want for this class? So what I want actually is you to do it at this procedure in R. And we're gonna do this in 4R. So don't get worried. So what I'm gonna do, so you have to pay attention to this. I'm going to do the example of this, and I'm gonna give you, and I'm gonna show you how to do in R and how to plot all this with the regression line, of course, and you will do it practically for any value of any variable, sorry. Okay, so let's start and go to our studio. So can you see this? Can you see this properly, or you need a higher font, higher size of the font? ¿Lo pueden ver? ¿Sí se ve? Okay. So in general, so I'm just clear this up, and what I'm going to show you is how to do in R. So I'm gonna actually create a here in this folder. Sorry, not this one. In this folder, I'm gonna create a script, and I'm gonna create a text document that I'm gonna call it. How you wanna call it? So we can call it fat cancer. Fat cancer. So this is the one. Okay, so we created. Oops, my machine is not the best one, sorry. Fat cancer. It's taking a while to make this one. So give it a second. Oh my goodness. Not good. Sorry, I don't know what happened here. Then I'm gonna close it. Oh, I think it got closed. Oh, it's because it's I thought, sorry. I don't know, this is weird because I was preparing all these things before. So let's see scripts, and then so it didn't respect my name. So fat cancer. Well, he doesn't like the name apparently. So forget about these things. Then I'm gonna do it actually in my documents. So here I'm gonna create a folder called scripts, script trash. It's trash. I need to do it later. So I'm gonna create a document, and I'm gonna call it fat cancer. have the here, and then what I'm just gonna do is actually take this too. Actually, I can take all of this. So I'm just gonna copy here, and then put it here, and then I'm gonna create a fat, and then I'm gonna say just cancer CDR, and then fat, so fat intake and CDR. So that's gonna be my data, right? So, and then I'm gonna actually create a model for a script in R. So I'm gonna create this script, just gonna save it. So just say like something like this script runs regression analysis using least square method. So here, so we save it, and then I'm gonna just save it in data, and the data is gonna be my scripts, and then I'm gonna call it FE versus CFD, like this. So this is, now it's here, you see? It's here, and then I'm gonna actually make the session to this, set my work on directory to the file location. It's already set. So here, I'm gonna read the data. So I'm gonna read the data, and the data is going to be equal to read dot, I think they call it read table, exactly. So I'm gonna create this one, and then I'm going to create the file. The file, it's already named as what was the name of the file? Fat cancer. Fat cancer of, and then .txt, comma, and then I'm going to use the header, and it's going to be true. And I'm assuming that that's it. So here we're going to run it. So the data is already here. So I have two variables, FID and CDR. So if we have two of this, so then we just can actually calculate. So let's just read it, put it here. First step, read the data. So read data. I'm going to create more like this. Author. Expecting you to do this like this. So Joseph now Revuelta, and then something like this, like I don't know, the date. It's going to be it's 05/13/2021. So this is, and then if I'm actually doing this, I'm going to probably say like assignment. I don't know, like 13, something like that, right? So I'm just providing the documentation. Let me just close the Telegram. So here you have the data here, and then we have the data, and then we're gonna make it, gonna compute to calculate the number data set, data points, or data pairs. So I'm gonna create a variable called n. N is gonna be equal to length, is length of data. And then if I create the length of data, I run it. So no, this is not length. So let me just run it, and then it's 2. No, it's not. So we're gonna actually use a command dim, and then 1 like this, and then n is gonna be 7. So if you actually do this, it's gonna be 7. So you just run it, yeah, 7. So now we have the length of the data. So what we can do is, of course, it's calculate. Remember, if we go to Excel file, calculate these values, x squared times y, x, y, and this, like this, right? So we have to calculate each of them as well. So to make it easier, right? So we can calculate each of them and we can do this like boom, but just do it in one operation. We can do that. It's up to you how you can do it. But I'm going to do it step by step just to actually show you how to do it. So calculate the how we call this, the elements of R. So here we have actually X. We calculate this one X. X is going to be, well, this is not, I don't know. Let me just, so yeah, of course, we can do this. So, sum of X, sum X, let's just calculate like this one. Let me just go and do this. Sum of X. Where is this one? Sum of data, and then we have this one, and then this is X Fi. Yes. So we calculate the summation of X. We run it, and then you see that the summation of X is equal to 568. So apparently it's correct. So now we can calculate actually the summation of Y. Summation of Y is equal to sorry, it's the basic keyboard. It's just making me crazy. Summation of Y. So it's going to be data, and then CDR. So we can calculate the summation of Y. Run it. Boom. It's 81. So it's 81. So, and then I can calculate of course, the summation of X squared and the summation of Y squared. So if we actually get this one, we have the summation of, we can actually put in parentheses data Fi squared. So this is the summation of this data squared. So let's just how it goes. Oh. Here. So it's 6,528. Oh, it's correct. So nice. So, and then the summation of this one, of course, I'm just gonna copy this to make it easier for me. And then this is gonna be equal to CDR. Oops, CDR. So, and then the Y squared run, and it's 1,433. So we have all of this. Yeah, it's that one. So now what we need to do is, of course, calculate R, because we already have everything we need to do, right? So then we calculate this one to number 4, calculate R. Sorry, R. So R is going to be equal to, if you remember, the formula is this one. So R is going to be equal to this. So R is going to be equal to parentheses. It is very important, of N, because we already calculated N times the summation. Oh, actually, I think I forgot one. It's the summation of XY, right? Yes, the summation of XY. So in this case, we're going to make this one very easily. And then the summation of data I times data X CDR. So now we got this one. So is this one the summation, and then I'm gonna run this one, and then the summation of SY is 9,089. So we have here, it's accurate, it's the same thing. So then we calculate, of course, n times the summation of xi, right? Minus the multiplication of the summation of x, summation of x. Oh, I think, well, it's fine. The summation of x times the summation of y. Okay, and then let's just change this one because I have to be consistent. We have it here, so summation of y, and then we just make this one another parenthesis, and then this is equal to another parenthesis, n times the summation of x squared, which is this one, sum x squared, right? This one is the one minus the summation of x, sum of x. Oh, I think this one is actually big one. Yeah, the big one. Yeah, I have here another problem. This one, oh boy. So I just change it to this one. I want to be more precise. Summation of x, x squared, summation of x, and then we have to make it this square, right? And then this is going to be times another parenthesis, which is n times the summation of y square, which is this one, summation of y square, minus this, the summation of y, and then this is going to be y, and this is going to be a square. And then finally, after these parentheses, which is this one, we have to actually make this one to the power 0.5. So this apparently, this is actually x. This is the value of r, sorry. I have to round all this up, run it, and then r is equal to 0.9529. So we'll see what happens. So 95.29, yeah, it's correct. So we have that r is equal to 95. So then we just need to finalize the values, and then you say like this one, and then we have to calculate. Well, we can calculate the standard deviation. Calculate B, A, and B, A, and B. So if you remember calculation of A and B, you have to calculate first B. So B is equal to R times standard deviation. I think this SD is the command. I don't remember, or STD. So I don't remember the standard deviation in R. I think it's SD. Yeah, in this is D. Then we calculate the standard deviation of R of X, of Y, sorry, of Y, which is the standard deviation. This is going to be data Y divided by the standard deviation of data of X. So this should be equal to B. So let's run it. B is equal to 0.18, 0.1875, correct. So we did things properly, and then we need to calculate A, and A is equal to this one. So A, if you think about it, A is equal to the mean of Y minus B times the mean of X. So it's going to be equal to the mean of Y, which is data Y minus, it's minus, right? Minus, yep, minus B times, oops, B times the mean of data, and it's F, like this. So A, it's equal to this. So, ta-da! So we have minus 3.9, so minus 3.9. So it's correct. So, and then finally, what we already have this one, all the values, and then we can calculate like R square gonna be equal to R, of course, square. That's it. So, and then I always recommend this one. So I always recommend this one because it's important to do it. So in general, I said like, sorry, no, print results. Print results. So what I do is just this one. So let's actually print this. Print something like this. We can actually print it like this. So hold on, the equation, the regression equation is, and then I just can actually do it like this, and then print another one, so print, and then we can print something like this, paste. And then I said like, so the equation is always equal to Y, if you remember Y. So paste is to string. So well, actually no, because this is Y equal to, we say actually now to a string, and then we just type, in this case, we have equal to A, all right, variable A, and then we can actually put another plus, and then to a string again, and then this is going to be B, and this is going to be X. So like this. So, and then if this actually goes well, so I can run this one, and then the equation is here. So this is the equation. And then if we actually make the separation, we can actually set like it's here, sep is equal to nothing. So we can rerun this one, and then, so this is the equation you see here. So, and then we can print something like this. The correlation, the coefficient of determination You say print. Same thing. So we just actually paste this one, paste. You actually say R squared. R squared is equal to comma to string. And then you just type R squared. So this one, you have this one, and then this one is going to be comma sep, and then you say nothing. So if we run it this again, so here you have this equation of determination. So this is what you need to actually print. So what I want you to do is exactly the same I did right now, but you have to apply it for all these exercises that I'm actually providing you in the assignment. This one, for this one, for this one, and for this one. So in general, so you need to give me an R script like this one. You already have this video, so you will watch it the times you want to do it. So, and you need to actually do this. So such as that when I review this assignment, I will review this assignment, of course. And when I check the assignment and I go to give you the qualification, the grade, sorry. So what I'm just gonna do for me in this case is just open a PowerShell script, and then I'm gonna say R script. Oh, it's not that script here. So give me a second. I'm gonna just do it very quickly. Environmental variables. So I'm just gonna make sure that. So give me a second. Where is R? No, R is here. So I'm assuming that it's been, yeah. So this is the one. Sorry, just my computer it's new, so I need to. So it's here, and then what I'm going to do is something like this. Something like this. And I'm gonna say just R script. R script. And I'm going to make this one a command. And then I'm gonna say like fi.r. So you see here, so when I type this one, what I'm going to get in actually is the regression equation is 3.934 for something point like this one. And then the coefficient of determination is this one. So that's what I want you to do for the assignment. You have to create an R square, and you're actually gonna give me, if you think about it, you're actually gonna give me the script. So that the script is gonna be actually applied for all of them, for all these exercises. It's going to be the same. So you only need to do one exercise, and then you just have to provide, of course, the different how can I tell it? The different inputs and the script that you already solved it. So you have to give me the 4 input files and only one script to run your data. Okay. So that's important for you to do it. So you have to give me only one script for me to verify all of this. Okay. So that would be your assignment. So do you have any question? ¿Alguna pregunta de qué es lo que tienen, de cómo hacer la tarea? Me tienen que dar solamente un archivo de R script, así como lo hice yo prácticamente, y que yo pueda verificarlo y correrlo en mi shell. Y prácticamente voy a checar que corra, y si corre, pum, tiene sus puntos, ¿no? Si corren, tiene su punto. Entonces me tienen que dar los archivos de entrada que ocuparon y me tienen que dar el script que están generando.
Tenemos que descargar R para hacer la tarea.
Pues sí, ¿no? Se supone, pues si no, ¿cómo lo va a hacer en R? Eso ya lo habíamos
Ok.
descargado desde la primera clase, ¿eh? Ya lo habíamos visto desde las primeras clases, lo descargamos. Tienen hasta un video,
Bueno,
creo, de cómo instalarlo.
Mm, bueno, ok.
Sí, Montoya, tú sí lo instalamos, ¿sí recuerdas?
¿Cuál, profe?
El R Studio, R Script.
Creo
R
que sí
Studio.
lo habíamos descargado.
Sí, lo habíamos instalado, de hecho.
Profe, entonces van a ser 45 que le tenemos que dar en un solo archivo, ¿no?
¿45 qué?
Es que dijo que le diéramos 45 resultados, creo. Algo así le entendí.
No, me tienen que dar prácticamente, o sea, que un script que tienen ustedes en R Studio, prácticamente tienen que dármelo así como yo lo estoy haciendo. Ya lo tienen aquí. Prácticamente sería basarse en algo que ustedes hagan, ¿no? Pero tienen que ser creativos, porque el R-Script que yo les estoy dando aquí, que ya lo pueden ver y pausar prácticamente para hacerlo paso a paso, tiene que ser general para todos estos ejercicios. O sea, si se dan cuenta, aquí la variable es XY y aquí la variable cambia. Entonces, por ahí ustedes tienen que checar que la variable siempre sea la misma, de tal forma que yo nada más lo que haga es cambiar el nombre en su R-Script, cambiar el nombre de su archivo. Yo lo único que voy a hacer cuando revise es que voy a cambiar aquí el nombre y voy a colocarle, no sé, file one o input one. Input one, y este sería en este caso, el input que me están dando sería el input one. En este caso sería prácticamente su primer ejercicio, Luego sería su segundo ejercicio. Pero recuerden que aquí solamente tienen que hacer la relación entre estos dos. No se preocupen por el año, ni se preocupen por el día. Pues tienen que hacer los ejercicios para estos y para estos. Ya de hecho les di una hojita de cómo se van a lucir, ¿no? Los resultados están aquí. Les dije, ya los tengo hechos. Si se dan cuenta. Así se va a ver y estos son los coeficientes, pero prácticamente ustedes me tienen que entregar un script en donde yo pueda hacer esto y revisarlo, ¿no?
Ok.
Vale, entonces, no sé si tienen alguna otra pregunta.
No, pues no. Ay, me voló.
Eso tienen que tipearlo a mano, ¿no? Ni modo, tienen que tipearlo a mano ahí, cópialo en Excel y ya lo hagan, ¿no? Entonces, pueden ir, pueden ir escribiendo mi script, lo más fácil, así como lo estoy haciendo, lo ven, y pueden ir prácticamente ir replicándolo, pero tienen que checarlo para que ustedes nada más tienen que cambiar script. Input 1 sería el primer ejercicio, input 2 el tercer ejercicio, input 3 el tercero, input 4
Que por cada ejercicio agregaremos como quien dice un bloc de notas, ¿no? Nada más para que lo vaya llamando, ¿no?
Así
Del
es,
archivo. Sí, es lo que yo estoy
exactamente.
entendiendo, ¿no?
Así
Entonces
es.
el programa lo único que va a hacer es ir extrayendo del bloc de notas la información y lo va a ir corriendo.
Exactamente.
Ya.
Pero, por ejemplo, aquí mi header es FI y CDR. Entonces, para ustedes, no vayan a poner esto, porque prácticamente se le va a poner problemas. Entonces, mejor pongan X y Y, XY, 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 para que no tengan ustedes ese problema, ¿no?
Sí,
De
sí.
estar cambiando las variables.
Ok,
Eso es todo.
perfecto.
Prácticamente, si pusieron atención o pueden ver el video, ya saben que está disponible en el Teams, pueden verlo cuando quieran.
Perfecto. Ok, ya.
Ok, ¿alguna otra pregunta? ¿Todo bien? Rivaldo, Montoya, Ángeles,
Todo claro,
Nayeli.
profe.
¿Todo bien, profe?
Perfecto. Entonces, ya nada más nos quedan, chicos, nos quedan dos temas, nos quedan numerical integration, numerical differentiation, y nos queda, por último, ver finite differences para aplicado a ecuaciones diferenciales. Entonces, nos quedan dos temas, prácticamente nos quedarían como yo creo que 2 semanitas o menos, de hecho, o una semana para que prácticamente no terminemos el semestre. Entonces, Ya estamos casi al final. Resistan y sean valientes. ¿Vale? Entonces, ahí nos vemos el día martes para seguir con el otro tema.
Bueno, profe, adiós.
Sale, profe,
luego.
cuídese mucho.
Nos vemos, Martín.
Hasta luego,
Dale,
profe.
igual para
Hasta luego,
ustedes,
profe.
cuídense. Hasta luego.
Sale,
Ahora
sale.